You're listening to a podcast from 702 and Cape Talk.
702 and Cape Talk.
The Naked Scientist.
Hello, Mr. Naked Scientist at Cambridge University.
Good morning.
I've got an accent like you, and I'm told that everybody here knows all about you and that you don't really need any introduction. I've listened to you plenty of times, I must say. So, Chris, I'm told about that there's something like a 3D bioprinter that can now build life-sized human organs. What have you got to tell us about that?
Yeah, well, just so that everyone in the know knows what's going on.
Yeah.
What we do is we say we say hello to each other awkwardly at the top of the show, which we have because we've never spoken before. And then once the awkwardness is out of the way, we think, now we need some people to phone in and ask us some good questions.
Exactly.
So to give the poor phone person a chance to pick up the telephone and find out if the people phoning up actually are just complaining, as usual, or whether they're complimenting you, which they probably are, or whether or not that they've got a good question. Then we fill with an interesting story which I've been spotting this week, and this is really good actually. This is a story which is in Nature Biotechnology, the journal this week, and it takes 3D printing to a whole new level, because in the past people are familiar with the idea of 3D printing. You can print stuff, you can print objects, you can print, even if you're a manufacturer, jet engine parts. Doctors have been printing implants for people based on scan data. Archaeologists even printed the skeleton of Richard III, the king who was found under a car park in Leicester in the UK. But the problem with all of these things is that they just print sterile stuff, which you then implant into the body to hopefully get colonised by cells or take over the function of, say, a missing piece of bone or something. What the dream here is to be able to print an organ, because we have a huge need for transplant organs, and we have to rely on someone donating an organ, either because they die or they have two of one organ and they give one of them away, like a living kidney donor. In all cases, though, it's not ideal. You're getting someone else's tissue, and there are all kinds of operative risks. Now, what would be really neat is if we had a way of printing cells into complex tissues, and then you can print complex tissues into organs. That's the dream. Well, it's come a step closer because Anthony Atala, who's a researcher at Wake Forest School of Medicine in America, their paper brings us really within the realms of being able to do that. They've developed this new 3D bioprinter where they have a series of nozzles which are loaded with a special hydrogel which prints a gel packed with cells, and different nozzles have different cell types, and they use a computer program to basically decide what cells to print where based on instructions that are fed into the machine. And alongside the cells are also printed a sort of cellular cement, which contains the same material that makes blood clot. So what you do is you print your cells in this special gel that supports them and nourishes them. You lay down a layer of this cement with them, containing the blood clotting chemical, and you also leave gaps between all of the cell rows so that you can have little pores running through the material so nutrients can diffuse through, rather like blood vessels. And then the real neat thing here is once you've built your thing you want to print, you throw on it and incubate it for a short time with the same enzyme that makes blood clot when a blood vessel is injured. It's called thrombin, and this sets the blood clotting material, making it cross-link like the glue, so all the cells are held in place. You then have a matrix that you can implant into the body, and the scaffolding you've printed the gel slowly degrades, what's left of it, and the cells are held in position and they naturally secrete their own supporting matrix, and they also grow new blood vessels and all that kind of thing. And in the proof of concept, they printed a piece of human jawbone, which looked pretty viable. They printed some skull bone for a rat, which they were then able to implant into the head of a rat. And 5 months later, they went back and examined the rats' heads, and the bone had integrated and knitted into the native skull bone and had its own blood supply plumbed in and everything. And they then print a muscle, and they actually print primitive muscle cells, make this muscle, and then wire it up to the nervous system in the legs of these experimental rodents. And this muscle responds to electrical activity and produces muscle-like electrical activity itself 2 weeks after they do this. So it's early days, but it's still an amazing step forward compared to where we were before. So we are now getting to within reach, possibly, of 3D printing things like kidneys.
That is fascinating and scary in many respects. Thanks, Chris. That really is very, very interesting. I've got a first caller on the line for you. Hazy from Grassy Park. Over to you to speak to the Naked Scientist.
Yeah, good morning to you. I like the way you say my name. I am Hazy.
Oh, Hazy. Sorry, Hazy.
It's
Yeah.
Hazy.
Okay.
I like Hazy
Good
too. I
morning.
think Hazy's pretty good. Morning.
When we think of a dripping tap, is
Yep.
a drop of water always the same volume? Because I think by the mere nature of the word drop, it reaches a volume which then would drop, of course, relative to gravity, at a certain point. Is the volume of a drop always the same? And if so,
right.
when does it become a droplet?
I think there's a computer called a droplet, isn't there? Maybe, but a raindrop will never become a computer droplet. But the answer is, yeah, they're pretty similar. The volume of a raindrop is about 0.5 milliliter to 1 milliliter. Raindrops haven't always been the same size, though. Researchers actually who are doing work in South Africa used fossilized raindrops to work out how thick the atmosphere was and what its composition was going back millions of years in the past, because there have been places in the world, including in South Africa, where there were rocks, including rocks covered in dust and ash, which made a very nice surface into which, when a raindrop came down, it made a little dimple. And as soon as those dimples got covered over, because the ash had set hard like concrete when the raindrop came down, the dimple pattern is preserved. And so you can see these raindrops from rainstorms that were raging millions of years ago preserved in rocks. And the size of those droplets, they found, corresponds to how thick the atmosphere is, because a thicker atmosphere retards the flow of the water droplet through it more than a thinner atmosphere. And the speed of a droplet falling and accelerating also dictates how big it can be before it falls apart and fragments. So a droplet is restricted in size by a number of factors, which includes how fast it's expressed from a tap, what the atmosphere it's falling through is like, and so on. But a dripping tap, I would think, probably if the pressure stays the same, pushing the water through the tap, and there's no other effects to account for, like no vibrations or anything like that, then it should reach a threshold size when the stickiness of the water molecules, the surface tension, which is pulling the molecules of water in the droplet together, that will govern how big the drop grows before it detaches itself from the tap and then falls. So that's why people used to, I think, also use these drips as a convenient kind of timekeeping device, because the droplets will be a consistent size each time under all other factors staying the same. So you can use it like a clock. So I don't know when a drop becomes a droplet, but I'll certainly see if there's any strict definition of how big a drop is. But you're looking at about 0.5 ml of volume to 1 milliliter for a really big one.
Thanks a lot, Chris. It's 10:14, nearly 10:15. You're listening to Cape Talk and Radio 702. My name is Mark Hayward. I'm standing in for Reedy Tlabi today. And 1, 2, 3.
702 and Cape Talk.
The Naked Scientist.
Good morning. This is Cape Talk and Radio 702. We're talking to a naked scientist in England. I always wondered why Chris is called the Naked Scientist, but maybe if we have time, he'll come and tell us whether he is indeed naked. But Chris, while you're thinking about that difficult question, Alex in Fourways has got a very big question for you. Alex.
Hi there, Chris. How are you doing?
Hi, Alex. I'm good. You?
No, good, thank you. Good. Chris, I was reading quite recently, and it sounds a little bit at the top, but there's something called LIGO, which apparently detects gravitational waves. I did do some research on Wikipedia, but I'm just wondering if you could just sort of explain it on the radio, just in sort of a man-in-the-street kind of way, explain how they measure gravitational waves and what it actually means for the man in the street, myself included. Can I listen on the radio? Is that okay?
Good stuff. Okay, no problem at all. We sort of briefly touched on this last week, but we mainly dwelled on the fanfare rather than on the nuts and bolts of how this works. You're quite right that LIGO, L-I-G-O, it's a laser interferometer gravitational observatory. That's what it stands for, and that's why they call it LIGO, because it takes too long to say the rest of the name. This is based in America. It consists of a V shape of pathways which are 4 kilometres long. So each arm of the V is over 4 kilometres of a trackway. I say trackway, but it's basically a tunnel. And at the apex of the V, where the two arms meet, a light source of laser light is injected there and split. So you have the same beam comes in and it's split into two, and one beam goes down one arm of the V and the other beam goes down the other arm of the V. When they get to the end of the arm of the V, which is over 4 kilometres away down this tube, there is a mirror there which turns the light around and sends it back to where it started. Now, all things being equal, the light, because the two arms are identical lengths of each other, the light should take the same time to go down one arm and get back to the apex as it does to go down the other arm and get back to the apex, which means the two light beams should arrive directly in sync with each other when they come back to where they started. And because of the way light works, it's waves. If you take a light wave going up and you add it to another light wave going up, then they make a brighter spot of light. If the light waves have travelled a different distance or taken a different amount of time to go down the two arms, they'll arrive out of sync. So one part of the light wave will be going up, while the corresponding partner light wave will be going down, and the two will add together to cancel out, and you get a dimmer patch of light. So the researchers can see if the light has taken the same amount of time to make the journey in each arm of the V. Now, the theory here is if a gravitational wave comes through, then because of the way the gravitational waves will change or distort the shape of the thing they're passing through, then this will stretch or shrink the path for the light in one arm of the V, and this means that the light will temporarily move out of phase, so that when it comes back to where it started, it will meet its brother or sister light beam slightly out of step, and this will change the brightness of the light in a way the researchers can record. That's the theory, and when they turned it on with some advanced detection machinery, it worked, and what they reported last week was this chirp that they detected corresponding to two big black holes orbiting each other and merging and producing a big load of ripples in space-time, which travelled for about 1 billion years across space till they hit the Earth, went through the Earth, and as they went through the Earth, they made this recordable change. Now, this is important, A, because it confirms the theories that Einstein suggested as part of his theory of general relativity 100 years ago, but it also means if we can extrapolate, exploit, and build better detectors, we can also examine the universe around us, not just using visible light, but we can also use gravitational waves to understand big objects in the universe, because gravitational waves, unlike light, which will be blocked by other objects that are in the way, gravity waves will come straight through those objects. So even if there's a big planet or a star in the way, we can still see those gravitational waves. They'll be potentially interacting with some things, but we should be able to investigate the universe in a whole new way, looking in the dimension of gravity rather than just light.
Thanks, Chris. What a world we live in, really. You're listening to 702 and Cape Talk. It's now 10:22 on Friday morning. You can talk to the Naked Scientist on 021 446 0567 or 011 883 0702. Or if you want to send an SMS, send the SMS to 31567 or 31702. We've only got a few more minutes left with Chris, so there's no time to waste. Chris, can I ask you a more mundane question, and it maybe applies to you as well? You know, I've lived in South Africa for 30 years now, but I still carry this strange British accent. Even though, you know, it's a long time since I went to school in England, and even though I was born in Nigeria, what is it that shapes the way we speak so early in life and means that we carry it for the rest of our days?
Well, we learn to speak very early on. If you think about it, your brain puts itself together, and without ever having to go to school, it teaches itself to speak a language by imitation by the age of 2 or 3. You've got hundreds of words, and you know how to make all of the complicated movements, and it really is a series of very complicated movements, because you've got to operate the nerves that open and close your vocal folds, your vocal cords, to make the vibrations that are the sounds. You've got to control your diaphragm, that expels air from your lungs at the right rate. You've got to control where your tongue goes, where your cheek muscles and other muscles of facial expression move your face in order to mould the sounds, to make the speech. You've got to do all that in the right order at the right time. It's a really, really complicated process producing the motor pathways and motor programs that enable you to speak. Now, in the same way that when you play tennis, you get better at it by practice, that's exactly what you're doing early in life. You're moulding your brain to become very good at producing these speech patterns. Now, the sound of speech is directly dictated by how you form the shape of your mouth. And those shapes correspond to the ultimate sounds that come out. And if you are immersed in people who you're copying, which is how we learn language when we're little, we just copy what everyone does around us, you're going to produce the same sorts of movements and face shapes to produce the same sorts of sounds as those you hear from people around you. So therefore you imitate the people and the sounds of the people around you, so you end up sounding largely like the majority of the people you're with. And if you're in a population where the majority of the people sound one particular way, you will optimize that pattern of movements to sound the same as them. And that's your accent. But as anyone knows, you can't teach an old dog new tricks. We're very, very good at learning stuff very early in life. And then the brain becomes a bit less plastic. It's much harder to unstitch the way the brain wires itself together as you get older. So, for instance, just by the age of 5 or 6, you can't teach yourself another language very easily anymore. You have to go to school and have a French teacher or a German teacher or an Afrikaans teacher who will then teach you a new language. Because your ability to just soak up languages by osmosis is less good than it was originally. And this is because the brain has begun to cement a lot of the pathways and the connections between nerve cells that correspond to those patterns of motor movements. And that's really why accents become so sticky. Some people, though, are much more able to catch an accent than others. And I have a very good friend. He lives in Australia, in Perth, where actually there's an enormous number of South Africans now. But my friend David grew up in Middlesbrough in the Midlands of the UK and Yorkshire, and he has an accent corresponding to the Midlands of the UK, and he's been in Australia for 30 years and does not sound any different than your average English sort of Middlesbrough man. Whereas I know other people who've been in Australia for 5 years and they sound as Aussie as the other people they hang around with. Same with South Africa. And it may well be that there's an element of empathicness here. Some people are very, very much better at mirroring behaviour in others. My wife is one of them, and so they catch accents very, very easily. And this is part of the sort of human interaction. When we're having a conversation with each other, we mirror each other's behaviour and activity and change the way we make facial expression, the way we respond. And so some people may be more prone to catching accents for that reason than others, because they mirror the movements the other person makes to make Chris. The sounds they make.
Thank you so much. I thought that was a silly question. You gave an answer that could take up a whole book and has told me something I never knew. Thanks. That's incredible. It's 10:26. We've got a few more minutes left with The Naked Scientist. This is Cape Talk and Radio 702. I'm going over quickly to Rueda in Rudaport. Rueda, what have you got to ask?
I want to know, after the very hot days we've been having, we have these terrible, terrible thunderstorms. You know, lightning, thunder, it's really unreal. And I know we were warned that normally after such, few hot days, this is bound to happen, but why?
Chris?
Hello. Well, the reason that we have vicious storms is because there's energy in the atmosphere. And the more energy there is in the atmosphere, then the more powerful a storm can become. So it sort of follows that if you have a period of intense heat, which is causing a lot of evaporation of water off of the ground into the atmosphere, then you've got a water-laden, warm, energy-rich atmosphere. That water will condense into big clouds, and the expansion of the gas as it rises up will make these giant clouds coalesce, and the updraft of the rising warm air will pull in lots more cold air from around, and this will also bring other wet air with it. And as a result, you end up with the perfect storm brewing. And it's the same sort of science that drives hurricanes in the Gulf of Mexico over the southern states of America and the eastern seaboard of America, because you have warm seawater which evaporates, causes rising warm air, and as it goes up, it then condenses. And so you've got a saturated, water-loaded air driven by nice warm ocean. and that then spawns a hurricane. So I suspect that that's probably what's going on.
Thanks, Chris. That's great. I think we've got time for one last person. Esma, I'm afraid we've run out of time to bring you in, but quickly, Derek in Weltevreden Park, how do trees know how to produce tannin?
How do they know how to produce tannin?
That's the question from Derek. Sorry, I stole Derek's question out of his mouth. But I don't even know if I pronounced it right.
It's not quite how the trees produce tannin, and when they're browsed by animals, and then the ones ahead produce tannin also. How do the ones ahead know to produce tannin?
Yeah, very good question, Derek. And the answer is that plants are all having a giant chemical conversation with each other. And it may sound bizarre, but when plants grow together in a field or flower bed or in a forest, then they are releasing molecules into the atmosphere around themselves, and other plants can smell or pick up those molecules and respond to them. Why do they do this? Well, it's like a danger signal. In the same way that if you're walking through town and then you hear a scream and you look around, you become alarmed because someone else is alarmed. And we're very sensitive to audio signals if we're humans. Well, plants respond chemically. When an animal grazes on a plant, when insects attack a plant, when a plant becomes stressed because there's not enough water or the soil is toxic to it, then the stress in the plant caused by any of those things leads to the direct release into the atmosphere of a cocktail of different chemicals. The other plants pick up that cocktail, and this drives or switches on growth pathways in those plants in order to encourage their cells to grow more, because they're anticipating being broken or eaten or damaged, and they're going to need more tissue or have their plant bodies growing to repair the damage. Also, they upregulate the expression in the plant of nasty tasting things or poisonous things, because that way, when the same animal comes through and then tries to eat them, it's going to think, ugh, I don't like the taste of that, and then it will ignore them. The plants don't turn those defences on all the time, because those defences use a lot of energy, which you could be putting into growing better, flowering better, and making more seeds and making more baby plants. So they upregulate their defences only when they need to, in the same way that we wouldn't want to go around wearing a suit of armour all the time, but except when it was beneficial to do so.
Thanks, Chris, and thanks to everybody who's called in to Cape Talk and Radio 702. Chris, if we had any more time left, I'd just ask you how it is that your brain holds all of this information and able to spit it out such a fluent, coherent way. But thanks very much. You can go back to your books now.
Thanks very much, Mark. It's been a real pleasure. It's been real fun. Thank you very much.
It's been fun. It's great for me too, Chris. It's nice to speak to you, and thank you so much. You've been a pleasure to listen to. So